Hi folks, we're going to take a look at the solutions to the second quiz for Unit 1. So first question here asks us to sketch an accurate graph of this function f, and it also asks us to show how 3 points on the parent function y equals x squared are transformed by this function f. Now, even though it's not asked for, I am going to describe these transformations, so just to review how we can describe these transformations. And the first thing to remember is to do the transformations in the correct order. So you have to do the multiplication ones before you do the ones that involve additions and subtractions. So here I see that the negative in front of the square tells me that there's going to be a reflection. So the first transformation that I'm going to describe is a reflection in the x-axis. Okay. Now the second one I'm going to describe is the other multiplication, and since it's being multiplied by 2, I know that it's going to be, first of all, it's a vertical stretch, but in particular it's going to be a vertical expansion. And remember that I want you to be specific, that we're multiplying the y values by 2. So the way we can write that down is we can say it's a vertical expansion by a factor of 2. Okay. Now we can take care of the translation. So it doesn't matter which order we do them in, as long as we do them after the multiplication. So I'll start here with the horizontal translation. And remember that for horizontal transformations, the effect will always be the opposite of the operation that you see. So since we see an x plus 2, we know we're going to be subtracting 2 from all the x values. So here we have a horizontal translation. And this is going to be 2 to the left. Okay, and the last one here is we have our vertical translation, and this is going to be 2 units up. So we have our vertical translation 2 units up. Okay, now we'll go and we'll transform the individual points. So I want you to start with your parent function of x squared, and we've picked 3 basic points to represent the function y equals x squared, and now we're going to transform them, but we have to do it in 2 steps. So first I'm just going to deal with the multiplications, so negative 2 times my square, okay, and here it's the y values only that are being multiplied by negative 2. So the x values won't change, okay, but 1 times negative 2, negative 2. Here, as expected, for the multiplication ones, the vertex won't change. So here 0, but 0 times negative 2 still remains 0. And then here the x value doesn't change. 1 times negative 2 is negative 2. And now I'll finally bring in my translations. So remember here, opposite effect on the horizontal one. So here I'll be subtracting 2 from the x value. So negative 1 minus 2 is negative 3. Oops. Ignore that. Okay, and here I'm going to be adding 2 to the y value. So negative 2 plus 2, 0. Here, 0 minus 2, negative 2. 0 plus 2, 2. Here, 1 minus 2, negative 1. Negative 2 plus 2, 0. And now that I have 3 points on the transformed function, I can draw my graph. Okay, so again, I'm going to try to, no need to use a ruler as long as it's relatively clear. Okay, make sure you identify the x and y axes, and make sure that you identify the scale. So I'll have them go up by 1 unit on each side. So here we have negative 1, 2, 3, 0 is 1 point. Then we have negative 2, 2. And then lastly we have negative 1, 0. Okay, and from here I can now draw a fairly accurate parabola. A good thing to do before going on to the next question is just make sure that this makes sense. Here, if we compare this to y equals x squared, some people like to draw that on the same graph. we see that it has been reflected. We see that it is thinner than the original function, which we expect with a vertical expansion, and we see that the vertex has been moved 2 to the left and 2 up, so our answer makes sense. Okay, let's move on now to number 2, see what they're asking us there. It says, what are the domain and range of the function f at x given here? So first thing to remember is that with a parabola, the domain, unless there's any restriction, okay, should always be all real numbers. Now what I'm going to do is I'm just going to draw a very quick sketch of this to help me out. So I'm not going to bother with the individual transformations, but I do see that it's a positive a value, so I know it's going to be opening upwards. And just very quickly, I'm going to see that I have x minus 48.2, so I know it's going to move to the right, and then minus 6, so it's going to move down. So my parabola looks something like this, and this will help me determine the range. So first of all, the domain is just x is the element of real numbers with no conditions. But let's look at the range now. Okay, and I see that it opens up, so it's going to have a minimum value, and my minimum value will be exactly the k value in my transformed function, which is -6. So just from this very quick graph, I can see that the range is going to be all numbers greater than or equal to -6. Okay, so y has to be an element of real numbers, but there's a condition, so such that y is greater than or equal to -6. Okay, so a couple of reminders here. Anytime you're talking about a set, I want to see the curly brackets. I'd like you to use the correct variable, in this case here, x for domain, y for range. Tell me that it's a real number in this case here, because it takes on a range of values. And if there's a condition, such as the range, make sure you show it correctly using your inequalities. In this case, greater than or equal to. Okay, and that's it. But again, see how useful the graph was to help us do this. So let's move on to the next one. Okay, so quadratic function below showed is used to model the number of fish in a salmon farm enclosure. So that's our y values, is the number of fish, with respect to time, which is our x values. What would be a reasonable domain and range for this model? Now, we just said that normally a quadratic function has a domain of all real numbers, but now there's some conditions that come in naturally. So let's take a look at our domain here. Okay? X represents time. So first of all, we know that we're not interested in negative time, but there's something else here. Let's look at the y values. The y values is the number of fish. Now, in this portion of the graph, does it make sense to consider this time which comes after that point? Not really, because the number of fish would be negative. So I don't want to consider any time where my graph has the number of fish is negative. So a reasonable domain would be in this portion here, where the time is positive and where the number of fish remains positive. So my domain would lie between 0 and 40. So here, x can be any real number such that, okay, x lies, and remember how we write that when we have this interval, is we put the lower number on the left, so 0, and the higher number on the right, 40. And well, 0 can be included because that's the start, so that's why I'm going to put here 0 less than or equal to x. And at 40 or at 40 seconds or minutes or hours, that's when we have exactly 0 fish. So I'm also going to include the 40. Okay, so this would be a reasonable domain for this scenario. So even though we drew a full parabola, I'm really only interested in this portion of the parabola, where time is positive and the number of fish is positive. And so using that same idea, we're going to write down the set for the range. So here y can be any real number, but yet again there's a condition here. Okay, I know I don't want to consider a negative number of fish. Okay, so nothing below 0, but I notice that I have a maximum value here, so I'm not going to consider anything above that. So we look here, so 3, 400, so that must be 350. So that means that is 450. So here we're going to have 0 less than or equal to y less than or equal to 450. Okay, so even though if this was just a parabola on its own, it would be anything less than or equal to 450, you have to reason out that we don't want to consider anything below 0. Okay, let's move on to the last page here. Okay, so they're giving us a function. Okay, and remember what this represents. This is like a recipe. It tells us whatever you see in the bracket is what you replace x by in your equation. Okay, so here we have f at negative x squared. So we go back to the recipe, and wherever we see an x, we are now going to replace it by negative x squared. So this is what I'm trying to determine. So what is that equal to? Well, anywhere I see an x, I instead now replace it by negative x squared. Okay, so this whole thing now is also squared. Minus 3 times, replace x by negative x squared. And notice how I always put it in brackets. That's to ensure that I don't make any algebraic errors. And then plus 5. And now we just have to be careful about our algebra. So again, first let's do the exponents. So we're not going to worry about this multiplication by negative 4 yet. So here you have negative x squared squared. So first of all, I see that this is negative. When I square a negative, when I multiply a negative by a negative, I get positive. Okay, so it's going to be a positive value. And here, when I take the square of a square, the rule is we multiply the exponents. So this ends up being x to the 4th. Here we have negative 3 times negative x squared. So again, multiply two negatives becomes an addition. Okay, and then plus 5. And now we can just finish off this last multiplication. Negative 4x to the 4 plus 3x squared plus 5. Okay, and since there's no more like terms, there's no more simplification that we can do. Now notice that our answer itself, our output, contains variables, but that shouldn't be very surprising since my input also contain variables. Okay, let's move on to the last question. Okay, so determine the equation for the function shown in the graph. Show your reasoning. Okay, so the first thing I'm going to do is I'm going to write out what a transformed function looks like, and we know that it has the form a times x minus h squared plus k. Okay, where a is the stretch, and if it's negative, it would also include a reflection in the x-axis. Okay, h represents the horizontal translation, but it's also the x value of the vertex, and k represents the vertical translation and also the y value of the vertex. So since the vertex is very easy to see, let's start with that here. And I see that the vertex is equal to, well, x equals 2 and y equals 1. So right off the bat, h is equal to 2 and k is equal to 1. Now because the parabola is opening upwards, we know that a is going to be positive. And now the last bit of work is determining what the a value is. And let's remember what our trick is here, is we look at the shape of the graph by seeing what happens as x goes up by 1. Okay, so if we were to draw y equals x squared, so be careful here, make sure you look at the scale. Here each line represents 1 unit, but here each line represents half a unit. So if I were to draw y equals x squared, okay, it would look like this. And how does x squared behave? As x goes up by 1, y goes up by 1. Let's see what this graph does. As x goes up by 1, we see that y goes up by 1, 2, 3. Okay? That means that we need to multiply our y values by 3. So a is going to be equal to positive 3. And so now that we have the 3 components in the equation, we can write our final answer, y equals 3, x minus 2 squared plus 1. Okay? And let's just take a quick look to see if that makes sense. So a is positive, makes sense because the parabola opens upwards. I see that it's thinner than what y equals x squared would be on this graph, so it makes sense that the a value is greater than 1. And I see that the vertex has been shifted to the right by 2 units, so x minus 2 here, and it's been shifted upwards by 1 unit, so that's where the plus 1 comes from. Okay, that's it for now.